Huh, it's flu season, isn't it? I think it is. Should I get my flu vaccines? Let me check. Who are you?
I am Father Time.
Really? We're just a part of your imagination, Matt. I am the voice of reason, and that is my twin brother, Bradley.
And I can help you guys with?
You can help both us and yourself by not getting the influenza vaccine.
And why is that?
Well, to be frank, it leads to autism, and they use aluminum. Like, who wants aluminum in their body? Why not just eat tinfoil then? Plus, our president, Donald J. Trump, agrees with me.
Right, and this is why you still live in Mom's basement.
So I shouldn't get the vaccine?
Hello? Did I not just say my name was a voice of reason? Can you pass me those over there? Thank you. Anyways, first of all, there's no proven correlation between vaccinations and autism. And secondly, that was an MMR vaccine.
Yeah, but what about aluminum? Do you know what aluminum does to your body? Do you?
No, Bradley, what does it do?
Exactly. We don't know.
It's an adjuvant. It's a compound added to your vaccine to make it more immunogenic or elicit a stronger immune response. You have a stronger metal concentration in your Frosted Flakes.
Yeah? Well, how do you even know the viruses even exist?
Oh, simple, Bradley. Here, let me explain. Friend, come here. He doesn't have a face, so don't mention it.
So, sight occurs when a photon from your environment bounces off an object and hits your retina. The information is then compiled in the brain, and there you have it, an image. The photon is the particle that carries visual information from the environment to you. Photons are small packages of energy. They travel as waves, and the energy they carry is proportional to their wavelength. The smaller the wavelength, the higher the energy, and vice versa. The portion of energy we can see, visible light, is here, roughly 400 to 700 nanometers in the spectrum. It can only offer a resolution as small as half its wavelength, meaning we can only see things approximately 200 nanometers in size. But what if we use something with a wavelength smaller than that of a photon? This is where electrons come in. Because they're so high energy, their associated wavelengths are small and can offer better resolution. Only problem is, how can we use electrons practically? Our retinas aren't exactly designed to handle them. The solution? Electron microscopy. In the technique of electron microscopy, primary electrons are shot at a single point on a sample surface. The sample surface is then excited and ejects secondary electrons. Those secondary electrons are then drawn to a detector by a potential. The detector then reads and relates the electron bounce-back intensity to a shade of gray. Every point scanned is then compiled into a black and white image, and there we have it, our electron micrograph. And that's how we can be certain these small-scale pathogens actually do exist.
Thanks for the explanation, friend. Here, Bradley, let me show you some examples of how we can actually image pathogens. This is an electron micrograph of red blood cells in the human body. And this is how red blood cells should look if they're healthy. Now compare this image to this electron micrograph right here, which is red blood cells that are infected with the influenza virus. Do you see the difference, Bradley? Do you? Well, if you still don't believe that we can actually image pathogens, look at this electron micrograph right here. This is an electron micrograph of a T4 bacteriophage, otherwise known as a pathogen that can actually infect other bacteria. And this should prove to you that we can actually image on the nanoscale.
And that's why you should get the flu vaccine.